When you think about climate change, your mind probably jumps straight to uh, car tailpipes, maybe power plant smokestacks.
Yeah, the usual suspects.
Exactly.
Yeah.
But what about the steel in your actual car frame?
Hmm.
Or the chemicals in, say, your cleaning products? Even the cement holding your house together?
Things we don't often think about in terms of emissions.
Right. These materials have this absolutely massive, often kind of hidden carbon footprint. So today we're taking a deep dive into industrial decarbonization.
Hmm.
It's not just a monumental challenge, it's also this huge landscape for innovation, for real transformative change.
And for this deep dive, we've pulled together insights from, well, a few key places. There's a fantastic McKinsey article specifically on green steel,
Okay.
then a really comprehensive guidebook from the U.S. Climate Alliance, and also a detailed roadmap straight from the U.S. Department of Energy on industrial decarbonization overall.
So a good mix of sources.
Yeah, together they give us, I think, a truly holistic view, not just where we stand right now, but also the pretty ambitious path forward we need to take.
Okay, so our mission for you today is to unpack the most critical pathways for slashing these industrial emissions. We want to uncover some genuinely surprising innovations already happening,
There are quite a few.
and also highlight the big, kind of unanswered questions that are still shaping this whole transition. So what does all this mean for the future of the planet and, the products that literally build our world? Okay, let's unpack this. Let's maybe kick things off with just the sheer scale of the problem here. When you hear about global emissions, it feels like the industrial sector sometimes gets a bit overshadowed, right?
It often does, yeah.
But think about this. The global steel industry alone accounts for 7% of all global greenhouse gas emissions. 7%.
That's huge. Just one material.
And right here in the U.S., the entire industrial sector,
Mm.
well, it was responsible for nearly about 30% of our total energy-related CO2 emissions back in 2020.
And that number translates to 1,360 million metric tons. It's a staggering figure.
It really is.
And the urgency here is, well, it's palpable. The science is crystal clear. We've already seen global mean surface temperatures rise by almost 1 degree Celsius over pre-industrial levels.
Almost a degree already.
Yeah. And knowing that, the scale of the challenge to hit the Paris Agreement's ambitious 1.5 degree target, it becomes almost dizzying. We need a 50% cut in global emissions
50%.
within the next decade.
And then net zero by 2050.
Okay, and here's where it gets really interesting or maybe challenging. We've got these really aggressive targets for cutting emissions.
Right.
Yet industrial production, it's projected to increase by over 50% by 2050.
The increase, yeah. That's the tension.
So without truly aggressive action, that means emissions could actually rise by more than 17%. How do we even square that circle? Massive growth, massive cuts.
Exactly. It means this isn't just about, reducing pollution a bit here and there. It's about fundamentally transforming how we make almost everything.
A total rethink.
Pretty much.
Yeah.
So given this monumental challenge, the obvious question is, where do we even start?
And our sources, they lay out what they generally call the 4 pillars. These are essentially the foundational strategies that, if we pursue them together, in parallel, offer our clearest path to net zero industrial emissions.
Okay, 4 pillars. What are they?
Think of them as the bedrock. So number 1, energy efficiency. 2, industrial electrification. 3, low carbon fuels, feedstocks, and energy sources. We can call that LCFEES for short.
LCFFES.
And number 4, carbon capture, utilization, and storage, or CCUS.
Okay, EE, electrification, LCFFES, and CCUS. Let's peel back the layers on each one. First up, energy efficiency. This feels foundational, right?
Absolutely. It has to be the starting point.
It's about just doing more with less energy from the get-go. I saw a great example, the U.S. Department of Energy's Better Plants program.
Oh, yeah, that's a good one.
It partners directly with manufacturers, aiming to cut their energy intensity by 25% over 10 years. And the results, they really speak for themselves.
What did they find?
Well, between 2011 and 2021, these partners cumulatively saved 1.9 quadrillion BTUs of energy
Wow.
and prevented 116 million metric tons of CO2 from hitting the atmosphere. That's a truly massive impact just from being more efficient.
And it's important to understand this goes way beyond just, optimizing energy use in the old ways
Um,
or turning off lights.
right, not just the simple stuff.
No, it's about leveraging really cutting-edge approaches, things like strategic energy management or SEM, which is about systematically hunting down and eliminating energy waste everywhere, and also fully embracing Industry 4.0.
Industry 4.0. We hear that a lot.
Yeah, using AI, the Internet of Things, to create these interconnected, self-optimizing factories and even whole supply chains. It's about fundamental systemic changes.
Okay, so if efficiency is doing more with less, the next logical step is doing it cleanly.
Exactly.
Which brings us to pillar 2, industrial electrification. This is about swapping out those dirty fossil fuels for clean electricity, right?
Yeah,
Especially for heating things up.
precisely. And it's a potential game changer for process heat. What's really interesting is that, according to the sources, about 30% of industrial process heat needs are actually at or below 150 degrees Celsius.
Okay, relatively low temperature.
Right. And that temperature range is perfectly suited for existing electric technologies we already have, like industrial heat pumps.
So we can electrify a decent chunk right now.
Potentially, yes. But the bigger implication here, the thing that underpins this whole pillar, is that it relies heavily on the continued greening of the grid.
Right. The electricity itself needs to be clean.
Exactly. Our sources suggest the U.S. electric grid could achieve CO2 emissions factor parity with coal sometime between, well, now and 2030,
Parity with coal soon.
and parity with natural gas around 2030, at least in the more advanced scenarios. So as the grid gets cleaner, the electricity used in factories becomes this progressively more powerful decarbonization tool.
Even if the factory itself doesn't change much else.
That's the idea. The fuel source gets cleaner automatically.
Okay. Pillar 3. This was low-carbon fuels, feedstocks, and energy sources.
LCFS.
LCFES, yeah. This one's all about swapping out the actual inputs, the raw materials, and the energy sources from high-carbon ones to low-carbon alternatives.
Hydrogen seems like the big one here.
Hydrogen is definitely a huge player, yeah, both as a fuel and as a chemical feedstock.
But isn't most hydrogen today made from natural gas? Which isn't exactly clean.
That's the catch. Most hydrogen today, so-called gray hydrogen, is made from natural gas, but it can be made cleanly green hydrogen from renewables, pink from nuclear, or blue from fossil fuels, but combined with CCUS.
Okay, so clean options exist. What's the problem?
Well, the real hurdle right now is cost. Clean hydrogen, particularly green hydrogen made via electrolysis, is currently around, say, $5 to $6 per kilogram.
And gray hydrogen.
Much cheaper. So the critical question becomes, how do we drive that cost down, ideally below $2 per kilogram, to make clean hydrogen truly competitive?
Big cost gap to close. A very big gap. Plus, there are other important considerations, around safety. Hydrogen is highly flammable, and also potential side effects like elevated nitrous oxide emissions, depending on how it's used. So it's promising, but complex.
Okay, and that brings us to the 4th pillar, carbon capture, utilization, and storage.
CCUS.
Right, CCUS. This pillar is basically about catching the CO2 emissions before they ever get into the atmosphere, like a safety net.
How does that work exactly?
Well, it involves capturing the CO2, usually from a concentrated source like a smokestack. Then you have two options. Either find a use for it, that's the utilization, for example, converting it into a liquid hydrocarbon fuel.
Okay, turn it into something useful.
Or the S, storage. Storing it long-term, deep underground in stable geologic formations. And this isn't just, dumping it somewhere.
Right. I imagine there are rules. Oh, absolutely. It's done under strict EPA Class 6 regulations. That means sites are rigorously selected, monitored constantly, and permanently sealed to ensure that CO2 stays safely locked away, addressing, major environmental and safety concerns.
Sounds like a big undertaking.
The infrastructure challenge is immense. We're talking about potentially vast networks of CO2 pipelines. One projection mentioned needing $28 billion just for the Houston port area alone to capture about 25 million tons of CO2 annually.
$28 billion for one area. Wow. And how effective is it?
Current tech can generally achieve an 85 to 95% capture rate, but ongoing R&D is pushing hard towards ideally 100%.
Okay, so those are the 4 pillars,
Yeah.
Foundational strategies. Now, how do these actually apply on the ground in specific industries? Let's maybe start with some of the biggest emitters, steel, for instance.
Yeah, let's look at steel. Today, the dominant method globally, and still a big part of U.S. production, about a third, is the blast furnace basic oxygen furnace route, the BF-BOF, highly emissive.
Okay, so what's the alternative?
Well, the McKinsey report we looked at suggests this really transformative idea, creating green steel hubs.
Green steel hubs, what's that mean?
The really striking aspect here is the concept of decoupling the initial iron making from the final steel production, separating the steps geographically.
Huh. How would that work?
You'd make green iron maybe as something called hot briquetted iron, or HBI in regions that have access to low-cost natural gas, or ideally clean hydrogen and lots of iron ore. Think places like the Middle East, maybe Oceania, South America.
Okay, make the iron where the resources are cheapest and cleanest.
Exactly. Then you'd ship that green iron intermediate product to regions that have abundant, cheap, renewable energy.
Ah, like places with lots of solar or wind.
Right. And there you do the final steel production using electric arc furnaces, or EAFs, powered by that clean electricity.
So it's not just a new process, it's like a whole reimagining of the global supply chain for steel.
It really is a radical rethinking of industrial geography, which of course begs the massive question, can we actually make the logistics shipping that intermediate product competitive enough economically to make this whole concept viable and truly reshape manufacturing?
Huge question. Okay, let's pivot. What about chemicals? You mentioned it's hugely diverse.
Hugely diverse. We're talking over 70,000 different products coming out of something like 11,000 facilities in the U.S. alone.
Wow.
And what's really significant here, perhaps counterintuitive, is that it's actually the largest energy user in the entire U.S. industrial sector if you combine the energy used as feedstock plus the energy for heat and power.
Bigger than steel or cement in energy use.
In total energy consumption, yes. And natural gas and other hydrocarbon gas liquids, they account for a whopping 85% of its energy sources.
85% fossil fuels. Okay.
So this presents a pretty unique challenge. The current low price of those fossil fuels makes low-carbon alternatives like green hydrogen or bio-based feedstocks a really tough economic sell.
The economics just don't work yet.
Not easily. Take modern ammonia plants, for example. Ammonia production is responsible for about 20% of the chemical sector's direct emissions. These plants are incredibly optimized and deeply integrated with natural gas-based processes.
Right, they're built around natural gas.
Exactly. So adopting clean hydrogen would require substantial, really expensive retrofitting. It becomes this complex dance between what's technologically possible and what's economically viable today.
Makes sense. Okay, what about industries maybe closer to our dinner tables, like food and beverage manufacturing? Seems less intensive, maybe.
Well, it might seem less impactful than steel or chemicals, but it still accounts for a non-trivial 6% of U.S. industrial CO2 emissions.
6% is still significant.
Definitely. And what struck me as interesting, a cool fact from the sources, is how uniquely dispersed these food plants are. They're spread all across the country.
Oh, right. Unlike, say, steel mills or refineries, which tend to be clustered.
Exactly. Much less concentrated geographically.
So how does that dispersion affect trying to decarbonize them?
Well, that very dispersion means that tailored, often site-specific solutions are absolutely essential. You can't just build one giant hydrogen pipeline network for them easily.
Right.
So opportunities look different. Things like deploying electrified ovens and fryers, using advanced heat pumps for that lower temperature process heat we talked about.
Okay. Electrification plays a role.
Yes. And crucially, reducing waste. Both food waste and packaging waste all throughout the supply chain. That's a big lever here.
Waste reduction. Makes sense.
But a key challenge, especially in food and beverage, is how do you maintain the absolutely stringent product safety and quality standards while you're integrating these entirely new technologies and processes? That's paramount.
Can't compromise safety or quality. Got it. Okay, rounding out our industry spotlight, let's touch on two more with particularly stubborn emissions: cement and petroleum refining.
Right, the hard-to-abate sectors. For cement, the projections show CCUS making the single largest contribution to CO2 reduction.
CCUS is key for cement. Why specifically?
Because a huge chunk of its emissions, maybe 50–60%, come directly from the chemical process itself, from calcination.
Calcination?
Yeah, that's when limestone calcium carbonate is heated to extreme temperatures in the kiln. The heat breaks it down, and CO2 is released directly from the rock itself. It's not just from burning the fuel to heat the kiln.
Ah, so even if you used clean fuel, you'd still have these process emissions.
Exactly. You can't simply swap out the fuel and solve the problem. You have to capture those process emissions. So looking at the bigger picture, the path to near zero emissions for cement involves using clean fuels like hydrogen or renewably sourced electricity in the kilns, plus CCUS to grab those process emissions.
Both fuel switching and capture.
Correct. Now, for refining, while petroleum refineries themselves account for about 5% of direct U.S. energy-related CO2 emissions.
Okay, 5%.
The really fascinating part is their deep integration with the transportation sector, which accounts for, what, 35% of total U.S. energy-related CO2 emissions?
Huge link to transportation.
Massive. So decarbonizing refineries isn't just about the emissions from the refinery itself. It has this enormous ripple effect on the downstream products, gasoline, diesel, jet fuel.
Right, the fuels we use.
So the strategies are complex, but one promising pathway mentioned is actually using captured CO2 maybe from the refinery itself or elsewhere and combining it with clean hydrogen to create liquid hydrocarbon fuels. Synthetic fuels.
So using CO2 as an input.
Potentially, yes. The technology exists, but again, like with many of these solutions, the cost is still prohibitive today. It presents a major investment hurdle to scale up.
Okay, so we've got these four powerful pillars. We've seen how they apply differently across key industries like steel, chemicals, food, cement, refining. But let's be honest, transforming global industry, it's not going to be a walk in the park, is it?
Not even close.
From your perspective, reading these sources, what's like the single biggest mountain these industries have to climb? The overarching challenge?
I mean, if I had to pick one, it's probably the high costs, especially the upfront capital investment.
It's a sticker shock.
Exactly. These transformative technologies, building new plants or retrofitting old ones with CCUS or hydrogen capability, we're talking billions of dollars upfront for major projects.
Billions with a B.
Billions with a B. And zooming out a bit, the implication is we desperately need smart, sophisticated financing concepts to make this happen. Things like blended finance, which combines public and private money to share risk.
Okay.
And also the continued growth of institutions like green banks. These are public or quasi-public entities designed specifically to finance clean energy and decarbonization projects. They've already catalyzed something like $7 billion in investment since 2011.
So financing is critical. What else? Well, then there's the sheer scale issue, right? You mentioned demonstrating tech in lab.
Right, that's a huge one too. Many of these decarbonization technologies, they've been proven conceptually, maybe demonstrated successfully in a lab or a small pilot project.
Okay, proof of concept exists.
But scaling them up reliably and cost-effectively for full commercial industrial level use, that is a whole different ballgame. It involves completely different engineering, supply chain, and risk challenges.
Which really begs the question, how do we actually de-risk these massive investments? How do we give companies the confidence to go first and adopt these technologies widely?
That's the multi-billion-dollar question, isn't it? And tied into that is the industrial heterogeneity we talked about.
Heterogeneity, meaning everything's different.
Exactly. Every plant, every specific subsector within chemicals or food processing, they're all unique. Different equipment, different processes, different economic situations. So you need highly tailored solutions, not just a one-size-fits-all approach.
It means so much more complex.
Definitely. And we absolutely cannot forget the workforce. This isn't just about technology and steel and pipes.
Right, the people involved.
We're going to need entirely new skill sets to build, operate, and maintain these new facilities and technologies. And crucially, we need to ensure a just transition for workers and communities whose livelihoods might be impacted as traditional industries change.
A just transition, that's key.
Yeah, it's highlighted in initiatives like the Biden administration's Justice 40 initiative, aiming to ensure benefits flow to disadvantaged communities. It's about fairness and making sure people aren't left behind.
Okay, so costs, scale, heterogeneity, workforce. It really sounds like research and development, R&D, is absolutely vital across the board here, both for near-term improvements and long-term breakthroughs.
Couldn't agree more.
What's the sort of key strategic focus for R&D according to the roadmaps? Where should the effort go?
Well, the Department of Energy's roadmap really emphasizes this dual approach, a balanced portfolio. We need to invest in near-term solutions that can give us wins now, things like advanced energy efficiency measures, maybe optimizing existing processes.
Okay, the low-hanging fruit, so to speak.
Right. But at the same time, we have to make those crucial investments in the longer-term, truly transformative technologies. Things like direct iron electrolysis for steelmaking or entirely new chemical pathways that bypass fossil fuels altogether.
The moonshots.
Exactly. The kind of high-risk, high-reward research that might not attract purely private funding today because the payoff is too far out or too uncertain.
So public R&D is critical there.
Absolutely. And it's also about leveraging cutting-edge tools using advanced computational computational modeling and AI for process optimization, developing novel, cheaper separation methods for things like CCUS or hydrogen purification.
Using tech to accelerate tech.
Precisely. And ensuring we consider the full life cycle of emissions, not just what comes out the stack, but the embodied carbon.
Embodied carbon. Explain that quickly.
That's basically the total greenhouse gas emissions generated to produce a product from raw material extraction through manufacturing, transport, everything. It's the carbon footprint embedded in the product itself before you even use it.
Got it. So looking at the whole picture. Okay, one last thing on challenges. What about those truly stubborn, hard-to-abate emissions? It sounds like even with all four pillars firing on all cylinders, some emissions might still remain.
That's a really crucial point, and yes, that's the reality according to the sources. Even with widespread deployment of efficiency, electrification, LCFS, and CCUS, some residual emissions will likely remain.
Why is that?
Well, it could be from very small, numerous, dispersed sources where capture isn't practical, or simply because current CCUS technologies, while good, might not reach 100% capture efficiency everywhere, all the time. Or some industrial processes might just be incredibly difficult to fully decarbonize.
So net zero might require more than just cutting emissions at the source.
Exactly. Looking at the broader implications, this means that to achieve true economy-wide net zero, we'll almost certainly need what the sources call alternate approaches. This primarily means negative emissions technologies.
Negative emissions, like pulling CO2 back out.
Precisely. Things like direct air capture, or DA, which uses machines to literally suck CO2 directly out of the ambient air. Or enhanced natural solutions like massive reforestation or soil carbon sequestration. We'll need ways to actively remove CO2 to balance out those residual emissions.
Wow, so it's reduction and removal.
Seems to be the consensus for hitting true net zero. And this brings up maybe the ultimate final challenge. How do we integrate all these incredibly complex systems, the energy grid, hydrogen networks, CO2 pipelines, DA facilities, reformed industrial processes? How do we make them all work together synergistically across different sectors for maximum impact and efficiency?
That sounds mind-bogglingly complex.
It is. It's a systems integration challenge on an unprecedented scale.
Wow, okay. What an incredible deep dive that was into industrial decarbonization.
Yeah.
Seriously. The groundbreaking idea of green steel hubs totally reshaping global manufacturing.
Yeah, that one's fascinating.
To, simple things like electrified ovens in food plants and hydrogen becoming this fundamental new feedstock and fuel. It's just abundantly clear that transforming these massive energy-intensive industries is a monumental undertaking.
Monumental is the right word.
But the sheer ingenuity on display, the innovation, the potential,
Mm-hmm.
it's actually truly inspiring when you dig into it.
Absolutely. What stands out most to me, reflecting on these sources, is just the sheer breadth of solutions that are needed. There's no single silver bullet here.
No magic wand.
No. It's everything from, tweaking energy efficiency on the factory floor, the small stuff, all the way up to radically reimagining global supply chains with those green steel hubs. It's this robust portfolio of interconnected strategies and technologies, and each one has a vital, unique role to play.
Yeah, everything needs to work together. And for you, our learner listening in, what resonated most from this deep dive? Perhaps it's the surprising versatility of hydrogen.
Could be.
Or maybe that idea of green steel hubs completely redefining manufacturing landscapes. Or maybe it's just the intricate, complex challenge of making the everyday products we rely on with drastically fewer emissions baked in.
And this really prompts a final thought, maybe a question for you to mull over. As consumers, how might our choices, even something seemingly simple, like consciously looking for and supporting products with lower embodied carbon.
Like reading the label if there's one.
Exactly. Maybe indicated by something called an Environmental Product Declaration, an EPD. How might those small choices scaled up subtly influence these massive industrial shifts? How much power do we have collectively to nudge these huge systems towards a net zero future?
That's definitely something to mull over until our next deep dive. Thanks so much for joining us.